and the Israel Institute for Advanced Studies for once again hosting us. As usual, all the logistical arrangements have been superb. Thanks also to Elhanan and to Drew Futenberg for helping me organize the intellectual content of the school. Thanks to all the lecturers who agreed to speak in the school. Our lecture fees are not very high, but about all that can be said for them is that they are fair. Everybody gets paid zero. Despite this, I'm impressed that year after year we get the very best people in the field to talk about whatever the subject is, and this year is no exception. And then finally, I have to thank all the students for coming, because it would be pretty lonely standing up here without you. So thank you for coming. Just a few words about the next 10 days. If you've seen the official schedule, you'll see that it's a pretty intensive program. Lots of lectures, tours, social activities. But probably the most important activity is not on the schedule at all, and that's informal interaction. It's a tradition in the summer school to have lots of discussions between lecturers and students, students and students, lecturers and lecturers. Do use the coffee breaks, the lunches, late afternoons for that. It's probably the most important part of the school. And as for the lectures themselves, it's another tradition of the school that you should interrupt whenever you want with questions, comments. So as soon as a question occurs to you, don't wait for the end. Ask it right away. In fact, without such questions, it's really pointless for us to come and give lectures in person. We might as well just video ourselves and send the videos in. So you have to do your part to make this school a school and not just a series of performances. And with that, let me turn to the first lecture. Normally what I do at the beginning of a school is to give an overview of the field, and the field this year is dynamic games. I'm not going to talk about dynamic games in general, though. I'm going to talk about a particular class of games, repeated games, because it so happens that Larry Samuelson and George Malath and Martin Cripps are going to be following immediately with some lectures on repeated games, mostly I think with incomplete information. And so I wanted to pave the way for those talks by giving you the basic background on classical repeated games with complete information and perfect observability. So that's what I will do today. And I will start with this game. I think you all know what this game is. The Prisoner's Dilemma. The Prisoner's Dilemma is very popular because it crystallizes the possible conflict between cooperation or efficient outcomes up here and individual or self-interested maximization, which leads to outcomes down here. So the unique equilibrium, the only Nash equilibrium of this game is for both players to play D. In fact, it's a dominant strategy for players to play D, but that leads to payoffs which are Pareto inferior to the cooperative outcomes. to 2. And for that reason, this game has been a workhorse in many fields, economics obviously, but in a number of other social sciences, and as Mikhail was suggesting, even in biology. So there's a large literature on systems biology and also evolutionary biology where the prisoner's dilemma plays a role. What I want to concentrate on today, though, is what happens when the game is repeated. Do we still have this conflict between efficiency and self-interested behavior? And the short answer is not necessarily. So let's imagine that this game is played over and over again. I'll look at discrete time, so it's played in period 1, period 2, etc. And players are now interested in their discounted sum of payoffs. So pi I t is player i's payoff in period t, and a player is now interested in the discounted sum of those period payoffs. So delta here is the discount factor. And the first thing to note, probably most of you already knew this, is that with repetition, we might get an efficient outcome, even in equilibrium, even when players are maximizing. And I'm going to be using subgame perfect equilibrium as the equilibrium notion here. So to see that you can get efficiency, let's look at an example. Suppose that players use this strategy here, which I'll call conditional cooperate. It means play C, the cooperative strategy, as long as no one has ever deviated from C in the past. So you keep playing C as long as cooperation persists, but if ever someone fails to play C, then you play D forever after. So that's sometimes called conditional cooperate, it's sometimes called a trigger strategy. The thing to notice about it is that if the other player is using this strategy and there have not yet been any deviations from C, you are best off using this strategy too, because if you use it, cooperation will persist forever. So you'll get a payoff of 2 in every period. And when we add up all of those 2's with the discount factor, we get a grand total of 2 over 1 minus delta. But if you don't cooperate, if you play D one period, well, you'll do better that one period. You'll get a payoff of 3 rather than 2. But forever after, you're going to get at most 0. So your maximum payoff from deviating, your maximum total discounted payoff is 3. And that means that you will not gain from deviating so long as 2 over 1 minus delta is bigger than 3. In other words, as long as delta is bigger than a third, you're not going to want to deviate if there hasn't been a deviation from cooperation previously. And the argument is even stronger if there has been a deviation. Suppose that the other player is conditionally cooperating, and there has been a deviation from D. Then if you use this strategy too, you get 0 every period. You have a grand total of 0. If you ever deviate, though, you're going to get a negative payoff. So in this case, regardless of what delta is, you're not going to want to deviate. And so we conclude that as long as delta is bigger than a third, this strategy against itself forms a subgame perfect equilibrium. And maybe this is a good place to pause just to make sure that everyone's with me. Are there any questions so far? I'm anticipating that this is review for most of you. But if it's not, please feel free to say otherwise. Well, sure. Delta has to be greater than a third. Now, it turns out that this is not the only possible equilibrium outcome. In this equilibrium outcome, players get 2 every period, but there are other possible outcomes too. Let's take a look at what they are. Here's a picture. This is payoff space. So the horizontal axis is player 1's payoff. The vertical axis is player 2's payoff. And what I've done here is to graph the 4 points of the prisoner's dilemma. So 2, 2, 0, 0, and then the off diagonal payoffs, 3, -1, -1, 3. And those payoffs plus convex combinations of those payoffs are the feasible possibilities in any given period. Now, it's pretty easy to see that in addition to 2, 2, one possible equilibrium outcome is for players to get 0, 0 every period. If the other player always plays D, the best I can do is to play D also. So the completely uncooperative equilibrium is a possibility. It's also easy to see that we could never have an equilibrium in which a player gets less than 0, because going back to the payoff matrix, if you play D, the worst that can possibly happen to you is that you'll get a 0 payoff. There's no way that there can be an equilibrium in which, on average, you're getting less than 0. So we can't have equilibrium payoffs below 0. But any payoff in this shaded region, that is, in the feasible set and Pareto dominating 0, 0, turns out to be a possible equilibrium pair, at least for a discount factor which is big enough. And let's see why that's for a discount factor which is close enough to 1. For sufficiently patient players. And let's see why that's so. Well, here's the formal statement. Pick any pair, V1, V2, in the shaded region. Then there will exist an equilibrium of the repeated game which gives you that pair of payoffs as average payoffs, provided that delta is close enough to 1. And there's a simple argument behind this claim. Actually, there are two simple arguments. First, I'm going to give you the simplest argument, or the simpler of the two, which supposes that players can make use of some kind of public randomizing device. Think of this as a public event like the weather, or think of it as some event like the closing Dow Jones average on the stock market. But whatever it is, it's a way of randomizing over these four vertices of the feasible set. So in each period, the public randomizing device will determine which of the vertices is going to be played that period. And if players choose the right public randomizing device, they can make sure that the expectation of that randomization comes out to be V1, V2. So in every period, there's a public randomization whose expectation is V1, V2. And in each period, players choose the actions leading to the vertex which has been selected. If anybody ever deviates from what they're supposed to do, we just go to DD, or 0, 0, for the rest of the game. And this averages out to VI each period for player I. And that's all there is to the argument. Any questions about this? Yeah.
This public randomizing device, is that the same device you're using each period, or do you have different devices?
For simplicity, let's suppose they use the same device each period. They could use a different device, but that's a needless complication.
IID, though.
It has to be IID, that's right.
Where does the dependency on delta show?
Sorry?
Where does the dependency on delta show in this argument?
Well, it comes back to the argument that that players will not want to deviate. If delta were very low, then and for example, player 1 was stuck at this vertex, he might be better off deviating and playing D, so he could get 0 that
Future
period.
punishment is not severe enough.
That's right. So delta has to be big enough so that the future outweighs the present gain from deviating. Yeah.
And does the argument works for x and y axes? So on the left and bottom boundaries of the set. So does the argument work for left and bottom boundaries of the set?
Oh, if you're on the
Yes.
for the prisoner's dilemma, it does. I mean, you can get the boundaries. In a moment, I'm going to go to more general games, more general repeated games, in which case it may or may not be possible to get boundary points. In the prisoner's dilemma, you can get boundary points as
But not
equilibrium.
with this argument. But you need something more complicated.
Yes, more complicated than this argument, but they're in the equilibrium set. Yes. Well, so the question is, how can the players guarantee that the public randomization will put them into the shaded region? The point is that the players themselves choose the public randomizing device. That's either a matter of discussion before the game is played, or it's a matter of tacit convention. But the randomizing device is specifically chosen not only to get you, not only to get you into the shaded region, but to get you the exact V1, V2 pair that you're aiming for. So players have to be careful to make sure they choose the right randomizing device. Okay, what happens if they don't have public randomization at their disposal? Well, they can still get all of these points in V1, V2, but now in order to average out to V1, V2, the averaging is going to be done through time rather than through randomization. So what players can do is, over time, to move among the 4 vertices. Maybe play here 1 period, and then maybe here 2 periods, and here 17 periods. And they'll choose how long to spend at each vertex in a way so that over time the discounted average payoffs turn out to be V1, V2. I'm not going to go into the details of how they can make sure that this can always be done, but I think probably you can see, at least loosely, why this is so, and there's a formal argument. If any of you are interested in seeing the formal argument, I can give you a reference on that. But it's very similar to the public randomization, except that now the convexification is done through time rather than through randomizing. Okay, so that's the prisoner's dilemma. But of course, players may not be playing the prisoner's dilemma. They may be playing a more complicated game. And we want to know what we can say about repeated games more generally. Well, what I've shown you for the prisoner's dilemma is an example of what we now call the Folk theorem for repeated games, which says that if we're repeating some game G and we focus on an n-tuple of payoffs V1 through Vn, which are feasible, that means they can be achieved by a convex combination of the vertices, payoff vertices of the game, and they are individually rational, which means that player I is getting more than his minimax payoff. I should explain this notation over here. Gi of Si and S minus I is player I's payoff in this game G if he uses strategy Si, and the other players, who I'll refer to as minus I, are using strategy S minus I. Now, what it means for player I to be minimaxed is that the other players are trying to hold player I's payoff down to the lowest possible point. Player I is maximizing against what the other players are doing, so player I will try to respond optimally to whatever S minus I is. But if we take the minimum of those maximizations for player I, we have what is called player I's minimax point. In the prisoner's dilemma, the minimax point was just 0. If player I played strategy D, that would that would ensure that player I got at least his minimax payoff, which was 0 in the prisoner's dilemma.
Or equal?
Sorry?
Larger or equal?
Well, actually, I want it to be larger. This gets back to the question that Kostya asked a few minutes ago. In general, it may not be possible in equilibrium to get all payoffs where some players are getting exactly their minimax payoffs. So for the purpose of the Folk theorem, I'm going to have a strict equality. It's a technical point, but one that is simplified by assuming a strict inequality.
Whether the others have a Republican domination or not, in S minus I, whether you are considering correlative strategy.
Oh, correlate, yeah. At the moment, well, actually, in general, I'm not going to look at correlated strategies. No. So the other players, the minus I players, are ganging up on player I, but in an independent way. If they're using mixed strategies, they're randomizing independently. Yeah.
Yeah, shouldn't you restrict the other players' strategies to also be individually rational for them? Is it possible for them to punish another player, but by using...
It is possible. It may be. Actually, that's a very good question. It may be possible for that to happen, but we'll see that we might run into problems with. So let's come back to that in a few minutes. At the moment, I'm not insisting anything. I'm not insisting on what happens to players who are punishing player I. They might be doing very badly. Anyway, the Folk theorem makes the claim that as long as players are getting payoffs that are feasible and individually rational in this slightly stronger than usual sense, there will exist an equilibrium, a subgame perfect equilibrium, in which on average they are getting VI every period.
You don't mean greater than or equal to?
I don't mean greater than or equal to, because it may be impossible to hit the minimax point exactly in some games. So rather than getting into when you can hit it exactly and when you can't, I'm just going to make life simple and suppose that this is a strict inequality. Because there's discount. Yes, if there were no discounting at all, then we could hit this exactly. But for my purposes today, I'm only looking at the case where there is some discounting. Maybe not very much, but there's some. Now, actually, what I've just stated is wrong. I mean, it is not the case for all games that all of these payoffs can be attained. And I'll give you an example of a game where this claim is false, but you'll see that there's something very special about that game. And so this claim is almost true, and we'll see the sense in which it's almost true in a few minutes. But first, to the counterexample. This is a three-player game. This is a three-player game where player 1 chooses rows, player 2 chooses columns, and player 3 chooses matrices. And I've indicated the payoffs that they get. Notice that this is a game of pure coordination. That is, whatever one player gets, the others get it too. And one thing you can easily check is that the minimax payoff for each player is 0 in this game. For example, if player 2 played the second column and player 3 played the first matrix, then player 1 would be confined to this column, and player 1 would get a payoff of 0. So 0 is the minimax payoff. And if the Folk theorem applied to this game, that would mean that any convex combination of 1, 1, 1 and 0, 0, 0 could be attained in equilibrium, as a subgame perfect equilibrium. But in fact, that's not true of this game. And in fact, there are no subgame perfect equilibria of this repeated game in which a player gets less than a quarter as an average payoff. That's the claim. So let me show you why this is true. Actually, before I get to that, is it clear what claim I'm making? Is the claim itself clear? Okay, so why is the claim true? Well, let me define alpha to be the lowest possible payoff that a player can be getting in a subgame perfect equilibrium, the lowest possible average payoff that a player can be getting in a subgame perfect equilibrium. It's the same for every player because the game is symmetric. And what I need to show in order to establish this claim is that alpha is at least a quarter. So how do we do that? Well, suppose that players in a particular period use strategies P1, P2, P3. So these are mixed strategies where player I is putting probability Pi on the first strategy. So either the first row for player 1 or the first column for player 2 or the first matrix for player 3. And what you can see is that regardless of what P1, P2, P3 are, there's always some player who can deviate and get at least a payoff of a quarter. So for example, suppose that P2 and P3 are both bigger than a half. Well then, if player 1 deviates and puts all of the probability on the first strategy, player 1 will get a payoff of at least a quarter. That is a half times a half. That's the probability of ending up at this vector of payoffs here. The probability will be at least a quarter if players 2 and 3 are playing their first strategies with probability at least a half. And similarly, if P2 and P3 were both less than or equal to a half, player 1 could deviate and put probability 0 on the first strategy. In other words, try to maximize the probability of being down here, which again will be at least a quarter. Well, I've done this for 2 cases, but you can see that there will always, it must be the case that if all 3 players are randomizing, that at least 2 out of the 3 must either be putting probability greater than a half, or both putting probability less than a half on the first strategy. So there will always be some player who can deviate and get at least a quarter. And everyone with me?
If one is already playing P1 with 1, why does it need to deviate?
Weak deviation. P1 prime could be equal to P1, that possibly equal to P1. I'm using deviate in an inverted commas, as they say. But as I said, somebody can always, at least one of the three players can ensure a payoff of a quarter that period. Let's focus on that player, the player who's guaranteed to get at least a quarter. And let's look at his discounted average payoff. Well, his total payoff is alpha, but this is a lower bound on his payoff. A lower bound on his payoff is alpha this period. I'm sorry, a quarter this period, plus delta over 1 minus delta times alpha. Remember, alpha is the lowest possible equilibrium average payoff that a player can get. And starting next period, a player will be getting an equilibrium payoff because we're looking at subgame perfect equilibria, so the game starting next period must also result in an equilibrium starting next period. The worst possible payoff in such an equilibrium is alpha, and so 1 quarter today plus delta over 1 minus delta times alpha tomorrow is a lower bound on a deviator's possible payoff. We can multiply this by 1 minus delta to get a lower bound on a player's average payoff. So this is a lower bound on the deviator's average payoff. And this has to be less than or equal to alpha. Since alpha is the lowest possible equilibrium payoff, implying that alpha must be at least a quarter. So when this game is repeated, despite the fact that 0 is the minimax payoff, we can never have equilibrium payoffs below a quarter. Now, what's going on here? What's the problem? And the problem is something that was already brought up in a question, which is if someone is to be punished, say by being minimaxed, for deviating, he's going to have to suffer, but so will his punishers. So if one deviates, one has to be punished. That means 2 and 3 might minimax him, but in order to punish player 1, 2 and 3 must also be harmed. Now, one way that we could try to avoid having 2 and 3 harmed, or one way we can try to compensate them for the harm that they are doing to themselves by punishing one is by saying that punishments should last for only a finite number of periods. So say 2 and 3, minimax player 1 for a limited amount of time, and then afterwards, players 2 and 3 get back in future compensation what they lost during the punishment period. That's a way we might try to avoid this problem of how do you get the punishers to punish. The problem is that in this particular game, you cannot have 2 and 3 rewarded after the punishment period without also rewarding player 1, because everybody gets the same payoff. So there's something somewhat degenerate about this game in that you can't punish one player without punishing everyone, and you can't reward some of the players without rewarding them all. The proposed solution that I've laid out here won't work in this game, but it will work in a lot of games. It'll work in the following class of games. So let me introduce a little bit of notation. Let's call V the convex hull of the feasible set. So remember the picture of the prisoner's dilemma. There were the 4 points, and we had all of the points in the interior. That's the convex hull. And we're just doing the same thing for a more general game. We're taking the convex hull of the feasible points, but let me normalize the payoffs so that the minimax payoff for each player turns out to be 0. We can always do that by transforming individual players' utility functions. So the minimax payoff will be 0. And now we want to look at what I'll call V star, which are the feasible payoffs, the payoffs in the convex hull, in which players are getting more than their minimax payoff. That's V star. And here is the crucial requirement. I'm going to require that the dimensionality of this V star be the same as the number of players. Now that was clearly violated in the 3-person example that we just looked at. In the 3-person example, the feasible set was a line segment which connected 0, 0, 0 to 1, 1, 1. In other words, the dimension of the feasible set in that example was 1, despite the fact that there were 3 players. But more generally, if we just picked a game at random, we would expect that the dimension of the feasible set would be equal to the number of players. Or put another way, that there will be that we can find payoffs in V star such that we can add or subtract epsilon from some or all of the players' payoffs and still be in the feasible set. So is it clear what I mean by the dimensionality of V star being n? But if it turns out that if the dimensionality is n, actually n minus 1 is good enough, but let me stick with n. If the dimension of V star is n, then we can use the idea that failed for the 3-person example. That is, we can punish players for a finite number of periods, and we can get the punishers to go through with the punishments by rewarding them after the punishment phase is over. So here is the correct version of the Folk theorem, or a correct version of the Folk theorem for games which satisfy this full dimensionality condition. Any vector of payoffs which is feasible and satisfies the individual rationality condition can be achieved as the average payoffs of the subgame perfect equilibrium for delta close enough to 1. And let me once again show you the arguments. Any questions about the statement? Is it clear what the claim is? So the argument will be constructive. We'll actually, for a given choice of payoffs, we'll actually construct an equilibrium which achieves those payoffs. And as what I was saying before suggests, there will be 3 phases involved in this equilibrium construction. First of all, there'll be what happens in the normal phase. The normal phase is what happens before anybody has deviated. And in this normal phase, players will, on average, be getting the target payoffs. Now, since in equilibrium they're not going to deviate, these will end up being the overall equilibrium payoffs. But then we have to look at punishments. Now, for the prisoner's dilemma, if somebody deviated, we just went to DD forever. So basically the same punishment was used regardless of who deviated and regardless of when that deviation took place. Now we're going to have punishments tailored for particular players. So there's going to be a punishment phase for each player I. But it's only going to last for a finite number of periods. And then after that punishment phase is over, there's going to be a post-punishment phase where the punishers are in effect rewarded for having punished player I, but I is not rewarded. And so it's the post-punishment phase which means that it doesn't matter how much the punishers are suffering during the punishment phase. They will still go through with it because they'll be getting this nice reward in the post-punishment phase, which will last forever. It'll last forever, that is, unless someone further deviates. So how do we construct an equilibrium with these 3 phases? Well, what we're going to do is, first of all, to choose payoffs in V star where players are getting less than the target payoff. The player I's target payoff is VI. We're going to choose a vector of payoffs where player I is getting a bit less than that, VI hat. So this just rules out the possibility that players may deviate and then be punished just in order to get VI hat, because VI hat is going to correspond to what player I gets in the post-punishment phase. We don't want him to be doing better in the post-punishment phase than in the normal phase. We also want to make sure that we can add and subtract a little bit, an epsilon worth of payoffs to each player's payoff and still be in the feasible set, because if it's player I who's deviating, we want to add epsilon to everybody else's payoff. as a reward. Now, how long do the punishment is the punishment phase going to last? Well, it's going to last m periods, where m is chosen to satisfy this inequality here. I won't explain exactly where this comes from yet. You will see where this inequality comes from in a couple of minutes. Let's suppose that the biggest possible payoff player I could ever get, regardless of what the strategies were, the maximum, the max payoff for player I is vi hat. We'll choose m to be big enough so that vi hat times m plus 1 is even bigger than vi bar. You won't see why we're doing this yet, but you'll see it very soon. So in the normal phase, now I'm going to construct each of these three phases, normal, punishment, post-punishment, explicitly. In the normal phase, we're going to do just what we did when we talked about the prisoner's dilemma. We're going to randomize over the vertices in such a way that the expected payoffs are the targets, v1 through vn. So each period, one of the vertices will be selected at random, and players are expected to play the actions which get you that vertex. If player I fails to do that, then we go to a punishment against player I. Now, for this purpose, I'm going to ignore what happens. Well, we're entitled to ignore what happens if players simultaneously deviate, because in equilibrium, they're not going to deviate at all. So how does punishment phase I work? Well, what will happen is that the other players, the minus I players, will just minimax player I for m periods. They will play strategies which hold player I down to a maximum of 0. And player I is in this punishment phase will be responding optimally to their strategies, so player I will in fact be getting 0 in each period during the punishment phase. If player I happens to deviate during the punishment phase, we'll just start that phase all over again. We'll go back and minimax him for another m periods. If
He's getting his V1. He can't be getting more than 0.
he can't be getting more than 0, but
So you can just ignore it.
yes, but there's going to be a certain repetition of the logic, which you will.
It's actually easier for you to describe the strategies.
It's easier to describe the strategies. It's also easier to prove it this way. There's not an additional case to consider. Now, what happens if one of the punishers, player J, is one of the punishers? If J fails to do his part in the minimaxing, we forget about the punishment against player I, and we minimax player J for m periods. Then after whichever player, oh yes, sorry, question. Well, what we're saying is if two players deviate simultaneously, we're going to pretend that they didn't, that nobody deviated. Now you might ask, well, can that be part of an equilibrium? And the answer is yes, it can, because if I and J are both deviating simultaneously, I didn't expect J to deviate, and J didn't expect I to deviate. In equilibrium, I is anticipating that the other players are going to use their equilibrium strategy. So he's going to be optimizing against their equilibrium strategies, not against a deviation. So there's no need to worry about what happens if there are simultaneous deviations, because that will never actually happen. Yeah.
What about if players can actually play, can actually talk and coordinate on deviation? Isn't this strategy very vulnerable to that?
Well, it depends. The hardline answer against your the hardline response to your question would be, players can talk all they want, but ultimately it's what they anticipate the other players will do that matters. You and I can say that we're going to be playing these other strategies, but we can't commit ourselves to doing that. We must always be optimizing. And so if players cannot sign binding contracts to do something else, then an equilibrium is an equilibrium, no matter how much they talk. Now, a more accommodating position is that, yes, players might be able to coordinate deviations, but in that case, what we're doing is refining subgame perfect equilibrium and obtaining what's sometimes called coalition-proof equilibrium. We can look at the set of coalition-proof equilibria as a refinement of subgame perfect equilibrium. I'm not going to talk about that today, but there is a literature on that.
And there is a folk theorem like that?
Well, coalition-proof equilibria actually can be restrictive. It depends on the game. In general, it is restrictive. Yeah. But you can show that if delta is close enough to 1 that you always get a non-trivial set of equilibrium. You get a multiplicity. It's not quite this multiplicity. Okay, so I was talking about the punishment phase, and I was saying that if someone deviates during the punishment phase, then that player is punished. If nobody deviates in the punishment phase, then we go to post-punishment. And in post-punishment, let's suppose that it was player I who was just being punished. In the post-punishment phase, players, the minus I players get rewarded. They get an additional epsilon added on to their payoffs. Player I, who is being punished, doesn't get rewarded. That would be counterproductive to reward someone who is deviated. So that's the construction, and all that remains to do is to verify that this construction actually works. I've described the 3 phases. Now I have to convince you that players will in fact not choose to deviate from this behavior, assuming that the other players are conforming to this behavior. Let me pause a moment, though, and just make sure that everyone understands the construction. I'd be happy to go over any details of the construction if it went by too fast. Yes? Well, this is similar to a question that was asked before about public randomization. In a sense, all of the equilibrium strategies are agreed to before the game. Otherwise, how would player I know what players minus I are going to do? You might say, well, they know it because there's a tacit understanding or from their experience in other games, but somehow or other, players have to anticipate before the game is played what other players are going to do. And that includes the length of the punishment phase.
Well, isn't that a fundamental problem, multiple equilibria altogether?
Well, this is the prime example of multiple equilibria.
Yes,
We have a huge right. So that's a problem. And there's a literature on how to refine. One of the things I'm going to do at the very end of the summer school is to talk about refining equilibria through some kind of evolutionary process. But in the classical theory, which I'm showing you today, we take equilibrium at face value, and if it leads to multiple equilibria, even a continuum of equilibria, so be it. That it's a problem, but without refinement, there's not much more we can say.
I think there's a problem with a single equilibrium also, but that's not about repeated games.
Yeah.
It's game theory.
You know, what this theory is not saying is how an equilibrium is. Well, several people have asked it. How do you agree on an equilibrium in the first place? The theory itself does not answer that question. There have been attempts to do that, but that's not part of this theory. So I have to show you that the behavior I've described, the three-phase behavior, constitutes a subgame perfect equilibrium. To do that, I'll have to consider deviations to make sure that deviations don't pay. Turns out we only have to consider a very special kind of deviation where a player deviates for one period and then conforms to the equilibrium strategy he's supposed to play after that. It's called the one-step deviation principle. If there exists any deviation at all that is profitable, there will always be a one-step deviation that is profitable. And so if we can rule out one-step deviations, we're ruling out all deviations. So let me prove, this is a little bit of a sideline, but let me prove the one-step deviation principle. That it suffices to pay attention just to one-step deviations. And there really are just two cases to consider. Suppose that a player had a t-step deviation that got him a higher payoff than he was getting if he conformed. So he's deviating for t periods, and then after that he's conforming. And t here is finite. Well, let's look at the last period of that deviation. Suppose that in the last period of that deviation, he's doing better than he would have done had he conformed in that final period, when we look at his payoff in that period and in future payoffs, in future periods as well. Well, then we've already shown that there is a one-step deviation that pays, namely the last period of the t-step deviation plus conforming after that. So that case is taken care of. What if there were an infinite period deviation paid. So the player is doing strictly better by deviating for infinitely many periods than if he conformed. Well, if he's doing strictly better by deviating for infinitely many periods, then because there's discounting, because delta is strictly less than 1, after a certain point, the additional contribution to his overall payoff must be tiny because it's being discounted by so much if we go to a very far distant period. So we can always choose a finite t big enough so that even if he just deviates for finitely many periods, he's still doing better than if he conformed. But then we're back to the first part of the argument again. And so this is a proof of the one-step deviation principle, that it suffices to pay attention just to one-step deviations. Now let's apply that to our three-phase construction. First of all, we have to show that a player will not want to deviate in the normal phase. In the normal phase, player I is getting VI every period, or at least VI on average every period. What if he deviated? Well, if he deviated, and we're only looking at one-step deviations, remember. If he deviated, he might do as well as getting VI bar in the period where he deviates. Remember, VI bar is the maximum possible feasible payoff. But then he's going to be minimaxed for m periods, so he's going to get 0 for the next m periods. And then after that, he's going to get VI hat. Remember, VI hat is what you get in the post-punishment phase. So let's compare this payoff with this payoff. Let's subtract this payoff from this. Well, if we look at this term here, we've chosen VI hat to be less than VI. So this part of the payoff is certainly positive. Also, if delta is close to 1, then this expression in parentheses is just a series of m1s, or m plus 1 ones. So this will be very close to VI times 1 plus m. And here we have minus VI bar. But remember, we deliberately chose m so that this expression would be positive. Actually, we chose it so that if we replaced VI by VI hat, this would be positive. VI hat is less than VI, so this a fortiori is positive. And so this entire expression is positive. In other words, it does not pay to deviate in the normal phase. You will be minimaxed long enough so that any possible gain is wiped out. And furthermore, your payoff after the punishment is over, it will be less than what you were getting before. So you don't want to deviate in the normal phase. Right? Any questions about that? Yes. Could you speak a little louder?
This m is moving with VI hat, right? Whatever the payoff I want to reach, the m is moving with.
The payoffs that we want to achieve are V1 through Vn. And yes, m might depend on V1 to Vn. That's right.
If I have a continuous payoff, I'm going to
Right. But all we're saying is that to achieve a particular vector of payoffs, we have to design equilibrium strategies which are suitable for those payoffs. Part of the suitability is the length of the punishment period. It would be too much to expect that the same punishment will work regardless of the payoffs that we're trying to achieve. So the fact that M depends on the target payoffs is not out of line with normal equilibrium considerations. I agree with the worries about how do you get to this equilibrium in the first place, and that's why later on I want to talk about how you might expect a repeated game equilibrium to arise at all. But for now, we're just going to accept standard subgame perfect equilibrium. If we accept that, then it's perfectly okay for M to depend on the payoffs that we're trying to achieve. So I've shown you, I hope you're convinced, that you don't want to deviate in the normal phase. Now, would you want to deviate in the punishment phase? Let's first look at whether player I, the player who's being punished, would want to deviate. If he doesn't deviate, he gets 0 for each period in the punishment phase, and then he gets VI hat. What would happen if he deviated? Well, if he deviated, the very best he could do in the period where he deviated is 0, because he's being minimaxed. He might get 0 by deviating. He might do even worse than 0, but 0 is certainly an upper bound on what he can get. Now, if he deviates, then according to the rules of the equilibrium, his punishment is restarted. So he's then going to be punished for M periods, and then we go to the post-punishment phase. Now, the upshot of this is by deviating, all he's doing is delaying this positive payoff for one more period. And he's not getting anything positive now.
One or more. That's one.
We're looking at a one-step deviation.
You might not deviate, it delays these for one or more periods, because you might not delay, hypothetically, you might not deviate at the first step of the punishment phase.
Oh, you're right. That's right. So yes, he might in effect be delaying his positive payoff even longer. Absolutely. So player I is not going to want to deviate. Now, but the whole reason for taking this approach where we reward punishers for punishing is to make sure that they are willing to carry out their punishment. So the crucial thing is to consider what happens if some punishing player, K, deviates. Now, during the punishment phase, player K could be doing very badly. Let's define V lower bar K to be the worst possible payoff that player K could ever get. It's the lowest feasible payoff for player K. And let's assume the worst and suppose that player K gets that terrible payoff for the entire punishment phase. Now, after the punishment is over, he's going to get VK hat plus epsilon. So remember, epsilon is the reward. Now, what happens if instead of carrying out this punishment, K deviates in the first period of the punishment? And the argument is even stronger if he deviates later. But he deviates in the first period of the punishment. Well, the best he can do is VK upper bar, the maximum feasible payoff. Then he will be punished for m periods, and then he will get vk hat. And what we want to do is to subtract this from this and hope that it's positive. If it's positive, then player K will not want to deviate. Well, a lower bound on the difference between star and double star is this expression here. M lower bar K minus v upper bar K plus the difference between Vk hat plus epsilon and Vk hat appropriately discounted. So that's does everyone agree with this? This is a lower bound on the difference between star and double star. But this expression is positive, and it's positive. Well, it's positive provided that delta is close enough to 1, because for delta close to 1, we can make this expression as big as we want. This expression goes to infinity as delta goes to 1, and so it doesn't really matter what's going on during the punishment phase. We can always outweigh it by the post-punishment phase, since the post-punishment phase is indefinite. And so overall, when delta is close enough to 1, player K does not gain from deviating. This, in some sense, is the most critical calculation of all, so I want to make sure that that you all agree with it. Are there any doubts? Okay, I will take your silence as a tacit yes. And the last thing to check is that you don't want to deviate in the post-punishment phase, but the post-punishment phase is essentially like the normal phase. I mean, you don't want to deviate there for exactly the same reason that you don't want to deviate in the normal phase. It's the normal phase with slightly lower payoffs than before. So I've got the calculations on the slides. By the way, the slides are going to be posted, I think, immediately, right? We can get these posted right after the lectures. Yeah. So the slides will be available for your scrutiny right away. And so I should have said at the beginning, there's no need to take detailed notes. Maybe take notes on the answers to questions, but no need to take notes on what I have up here, because you can just read it all. So we're done. I mean, that really is, that's really all there is to this folk theorem for repeated games with discounting, assuming complete information. We'll soon see what happens without it, and assuming that players can observe deviations. This is a good place to pause again. I'm going to go for a few minutes more, but this is a place where you should definitely ask questions, both technical questions and philosophical questions or objections. Yes. Phil?
This is not, well, this is beautiful stuff, but something that came up in the discussion of this and in the question is this matter of how you get to equilibrium, yes?
Right.
And actually, I think not only in repeated games and not just
right.
in one-shot ordinary Nash equilibrium,
right.
yes?
Right.
The problem of how you get there,
Yeah,
yes,
right.
and why go to equilibrium
Right.
is a problem that it's out there and it's
Yes.
been discussed
Right.
in recent years more and more, I think, that's what we say, searchingly, okay?
Right.
And it's a subject of discussion. It's
Absolutely.
not obvious
It is not
It's
obvious.
not obvious that rational people or
No.
rational utility maximizers
Right.
would get to Nash equilibrium.
That's right. And even more so, perhaps, if they're not rational utility. Next one.
Those are another kashi, but that's,
Or-
we're not talking.
Oh, no. I even Nash talked about that.
What?
Even Nash talked about.
Non?
Yes. If you look at his interpretation, so roughly speaking, there are two ways of interpreting a Nash equilibrium or subgame perfect equilibrium. One way is to think of it as a self-enforcing agreement among rational players.
But even that is down.
Yes, I know, but it's doubtful, but there's at least something to it. Yeah, in fact, you have the famous example with the 99877.
The stack on it.
Yeah. If players somehow find their way to these equilibrium strategies, no rational player has the incentive to deviate, and that's the idea behind the rationality literature leading to Nash equilibrium as a solution concept or as an equilibrium concept. There's another literature which says, suppose that players learn from experience. So they've played this repeated game, not just with their current partner, whoever that happens to be, but they played it in the past, and they've learned from their past experience or from society's past experience what strategies work well and what strategies don't work well. That's Nash equilibrium as a social norm, and there's a large literature on that too. It's that second literature that I want to come back to later in the summer school. I'm going to try to convince you that if you look at repeated game equilibria, social norms, you actually get something sharper than the Folk theorem as a prediction. But none of this is settled, and I definitely take Bob's point that our most fundamental concept in game theory, Nash equilibrium, is still questionable. It really depends on the circumstances. In some cases, it's a very good predictor, in others, less so. In the
Eric,
yeah. Oh, I'm sorry.
No. I believe that we finished. No, I just maybe.
No, we can go back. That's okay.
Okay, so my question is whether if the players can observe the payoffs, not completely surely, but there is an epsilon possibility of error and everything is possible, then does it radically changes the picture or not?
Players observe their own payoffs or other players?
The other
Well,
players
all right.
payoff with epsilon possibility of error and everything is possible.
No, even an epsilon probability that the other player might have different payoffs can make a big difference. And I think we're going to be seeing that pretty soon, right? Are you, in a few minutes.
No, I'm going to get coffee first.
Well, it depends what you mean by a few. Yeah. Yes. No. So actually, I was going to make this point. Anyway, so I'm glad you asked that question because I want to talk a little bit about finitely repeated games, but also about exactly the point you raised. First, let's suppose that the prisoner's dilemma is repeated not an infinite number of times, but a finite number of times t. What you may have already anticipated about that, and probably a lot of you have been shown this before, is that repeating the prisoner's dilemma a finite number of times doesn't change the uncooperative nature of equilibrium. There's a unique subgame perfect equilibrium of the t-period repetition of the prisoner's dilemma, namely to play d every period. And the argument is extremely simple. In the last period, we know that players are going to play dd. But if we know that they're going to play dd in the last period, they'll do that in the next to last period, because nothing they do in the next to last period can affect the last period at all. So you can look at the second to last period in isolation, and so on back to the beginning of the game. So players will play dd in every period in equilibrium. And that's true. The same principle is true for any game with a unique Nash equilibrium, like the prisoner's dilemma. If you repeat the game for t periods, you just get a t-period repetition of the one-shot equilibrium. So there's a discontinuity at infinity. For any finite t, we get this one equilibrium, but once we get to t equals infinity, then we get a whole huge set of equilibria coming in. And that discontinuity might be disturbing to you, as it probably should be disturbing. And anytime the parameterization gives you such an abrupt change, you worry about whether you've captured everything. Now, one way of smoothing things is to introduce incomplete information. If you introduce incomplete information, even a little bit, for a long but still finitely repeated game, you can get additional equilibria. And Larry, I think, is going to be talking about that. Now, another way that you can smooth is by supposing that this terminal date, t, is not itself sharp. Perhaps you know that the game is going to end eventually, but you don't know exactly when. And in fact, what we can do is we can reinterpret our discount factor delta as the probability that the game goes on for another period. Suppose that we do that. So now that, let's suppose that there's no discounting per se. Delta is simply reinterpreted as the probability that the game continues. Now, in this reinterpretation, the game will, in fact, end, at least with probability 1, in a finite time. But in all of the results that we obtained for the infinitely repeated game now apply to the finitely repeated game, because the terminal date is not sharp. Now, a third way that we can smooth things over, and this is work, I should say, that's due to someone in the room, Vijay Krishna and Jean-Pierre Benoit. Suppose that the underlying game G has multiple equilibria. So that was not true of the prisoner's dilemma, but there are plenty of games which do have multiple equilibria. Suppose that G is some game with multiple equilibria, and that's repeated. Then it turns out we get, in effect, the Folk theorem even with a finite number of repetitions. And because time is running out, got 3 minutes left, I think. I'm certainly not going to try to prove the full thing, but I will give you a flavor of the result. This is a game, a two-person game, in which there are, you can verify, there are two Nash equilibria. There are two pure strategy Nash equilibria. This is one, this is one. But neither of those equilibria is efficient. This is better for both players than either of the Nash equilibria. Now, suppose that we repeat this game many, many times, but only finitely many times. Then the argument is that despite the fact that 3-3 doesn't correspond to a Nash equilibrium of the one-shot game, it's still attainable as a subgame perfect equilibrium of the repeated game. And here's the idea. In all but the last two periods, let's say the last 4 periods, players are supposed to play U and L, which will get them payoffs of 3. So in a large number of periods, they're going to be getting 3-3. Now, what happens if player 1 deviates from U? Perhaps he plays M and gets a bigger payoff that period. Well, then we'll go for the rest of the game to BR, which is a bad Nash equilibrium from player 1's point of view. He's only getting a payoff of 1. And similarly, if player 2 deviates from L, we're going to go to MM, which is the bad equilibrium from player 2's point of view. If neither player deviates, then we have to do something at the end of the game which forms an equilibrium. Playing UL in the last period is not going to work because UL is not a Nash equilibrium. But what players will do is in the final 4 periods, half the time they will play MM and half the time they will play BR. So they're going to each average out with a payoff of 3 halves for each of the final 4 periods. It's just a matter of calculation to verify that if these are the strategies players are using, no one is going to want to deviate. You see, if you stick to what you're supposed to do, you get 3 for a long period of time, and then you get 3 halves on average in the final 4 periods. If you deviate, you'll get an immediate gain, but then you'll get a very bad payoff, 1, for the rest of the game. So you don't want to deviate. You don't want to deviate when you're supposed to be playing UL, and you don't want to deviate at the end of the game either, because in the last 4 periods, players are playing Nash equilibrium strategies every time. Yeah.
Are you talking about subgame perfect?
Yes, subgame perfect.
Equilibrium?
Subgame perfect equilibrium. Yeah.
So this requires that for each player there is more than one equilibrium payoff for
Yes.
that player, right? So
Yeah.
it's more than just a multiplicity of
That's right. There have to be multiple. Basically, there has to be a way of punishing a player in a Nash equilibrium. That's right. Any other questions?
What happens without the subgame perfect restriction when you have a finite number of periods?
Then there are some games for which, even if there's a unique equilibrium, the Prisoner's Dilemma is not one of them, but there are other games where there's a unique Nash equilibrium and you can get multiple Nash equilibria when that game is repeated. But they're not subgame perfect.
If I remember correctly, I think the condition is that each player gets more than his max min at the equilibrium.
That sounds plausible. Does that sound plausible to you, Vijay? Okay. Good. That's reassuring.
Okay, I suggest we let you have coffee because
Okay.
we're going to resume
Yeah.
at 4:30.
Class dismissed.